So I'm going to talk about this title, tensor graph decompositions for temporal networks. I've been working on this with Elvin of late. And yeah, so let's dive into the main talk. So dynamic networks are, well, essentially the way we can look at it is you have a topology, and the topology is essentially changing over time. And there have been quite a few ways people have looked at dynamic networks. There are some model-driven networks which approach the problem more from a network science perspective based on edge rewirings. And of course, like Alberto mentioned, there's another class of approaches which try to infer the dynamics from data. And sometimes these settings are also affected by a lack of observed data or a lack of data in itself. So like if the network is changing and we can't always observe some of the interactions between people due to privacy or similar reasons. So one way to look at dynamic networks is this particular paper, which works with MRI data, and they show that there is a type of time-varying topology which incorporates switching of connectivity patterns. So essentially, if you look over time, you'll see that there are a few functional networks which are not present at the same time, but over certain amounts of time, one of them is likelier to be present, as you see, because they have some probability of state activation. And so you have, so essentially the big picture from this slide is at a certain time, you can have different networks. Some of them are present, some of them are not present, but these networks are essentially contributing to the dynamics in some sense. A more simpler example also involving humans is a communication pattern over a set of people. So this can be, in its simplest sense, email communication between people in an organization. So over time, you see like employee 1 and employee 2 say like on day 1 they did not communicate, but on day T they did. And suppose on day capital T, employee 1 communicated with many people. So and there are lots of data of this type, which essentially deals with human communication, which you can also see that the network is indeed changing. So what do we do with these networks? Like one way to represent this network is through three-dimensional tensors, where on each time instant we have the adjacency matrix or some kind of matrix representation of the topology. And when you have these kind of tensors, well, one of the main advantages of using tensors is you can use tools like tensor decompositions, which kind of represent these tensors in different ways, of course. And of course, so once you can have tensor decompositions. However, if we want to interpret the dynamics, and that is something we want to look at in this talk, most of the work which does tensor decomposition on this type of tensor representation, they are mostly focused on generating embeddings for the nodes. And these embeddings usually are in some Euclidean space. They might be difficult to interpret, or they're optimized in a way that, okay, I want to solve this task down the road. How do I do this embedding? Sure, you can do it. And however, these decompositions are low rank. And if we want to look at the dynamics solely in terms of networks, then these low rank structures may not always be able to recover networks. Like by networks, I mean how a typical graph looks. And yeah, and that precisely brings to the point that they're not always interpretable as a graph structure. Because if you imagine an outer product between two vectors, it has a very constrained structure in it. And of course, sometimes the data may not also be available, so you can't use additional data to aid whatever task you're doing. So keeping all these things into account, what we want to do, or what we propose rather, is a two-way decomposition of this dynamic tensor we gave. And we want to break down the observed dynamic evolution as a sum of other tensors. But now each tensor is now corresponding to a different adjacency matrix. So essentially, what I want to do here is express the evolution of the structure as a sum of networks which can collectively capture this evolution. Illustration. So we have that same tensor, but what we want to do now is see, can we express what we have on the left as, okay, this one network, and yeah, so certain number of networks, let's say, and this ties into that example of brain networks where we had certain components. So you can kind of think of it like this. Now, and we also have this vector along with each network sticking out. So that is essentially like a time component which will scale the network and see how this network is essentially contributing to that thing. It's not exactly a classical tensor decomposition, but we feel it might give more interpretability in terms of that disintegrated structure. So on to some of the technical aspects. So we have this temporal graph, sure. So we come to this adjacency tensor, n by t. We observe t snapshots. Get that? Okay, we have this tensor. Good. And of course, we want to represent this as a linear combination of R. Ideally, want this to be quite small. Modal graphs, maybe we get them. And yeah, so we're kind of interested in finding this different ARs now. And the C's are the time vectors which capture the effect of time. And so given X, we want to approximate this X hat in this fashion. And this is essentially another way to look at this at a particular time. That adjacency matrix Xt is a sum of certain adjacency scaled adjacency matrices and another matrix T, which can be unknown dynamics or we have edge addition removal. It's something we're not particularly interested in for this topic. Okay, so the general idea is, given X bar, we want to find A and C, and this is formulated as an optimization problem. And we are going to just go one by one how we set this problem up. So L is a data fitting term, so we're given X bar. So usually we stuck for the Frobenius norm square, which is quite common in this field. And S is a set. So S is like, we want each adjacency matrix to have certain properties. So when you want properties, those properties are embedded in that set essentially. And we want each adjacency matrix to be sparse. So we impose the L1 norm on this AR through this G for each of the R's. We also have this function HA, and this HA, I want you to think of this as a constraint which looks at all the adjacency matrices as a whole, in the sense of what kind of relationship do we have between them. Are they similar? Are they very different from each other? In this particular talk, I'm going to focus on an HA which penalizes shared support across modes, which means that if you have a particular mode with a particular interaction, the rest of the modes will not have that interaction. That is what I mean when I say HA is penalizing. And of course, it's penalizing. It's not a strict penalizing, because this is a regularized problem. So once we have these things, and we have another function which constrains the C, which is the temporal variation. Now, depending on the application you are working with, you can have different types of Cs. In our case, we go for a smooth C. So each component is not changing a lot in time, like its time component is not changing a lot in time. But if you want the component to be sparse, like if you want it to not change in time, you can give a different function. This is a very general framework, so you can play around with it. Okay, so once we have these things, of course, this putting things in perspective. And okay, so how to solve for it? Well, there are, I'm omitting all the details here. So essentially, we do an alternate minimization between A and C, because this is not well convex in A and C. So and alternating methods work fairly well. So for each A, we again try to find each AR separately, and we do this in the dual domain, and they all converge because we're solving a concave problem there. And then we go to C. You see that C is easier. We have Frobenius norm squares. We have a closed form object for C. Okay, now results. First experiment, we have two graphs here. SBM is a stochastic block model graph, which we rewire in terms of generating the dynamic tensor. And the enron is dataset is employees exchanging emails. So we have around 150 employees observed over a 150 time period slot. So we have that, and the methods we have here is PGD is what we do. Second column is when we enforce more graph structure through the regularization parameters. Uncon is just the unconstrained problem, like, well, if you were just to solve the first term there, then you have uncon. And then we compare with the block term decomposition and the symmetric block term decomposition. So this is a standard low rank tensor decomposition. And what we do here is, in this table, we show the NMEC scores. So we see that, like, right away, unconstrained problem always is going to have the lowest NMEC, but it does suffer a bit when it comes to the, well, yeah, okay, we are going to come to that later. But in general, the NMEC here is a bit lower for the unconstrained problem. And imposing more graph structure, more constraints, so the error is expected to increase, and we do see that here. And then second, so now what we did was we evaluated the F1 score, and the F1 score is a measure of how well can you, like, recover lost unobserved edges. So we remove 20% of the observations from the dynamic tensor, and then we use all these models and see, okay, how much of this can you detect? And in general, we see that even though, of course, unconstrained is low error, or of the, like, no, in this case, of course, unconstrained has low error in the previous case, but now in the F1 scores, the PGD methods seem to do better overall. Then and of course also the BTD and SPT methods, because they don't really have constraints. And in the third case, what we did was we selected a set of nodes and we removed all of their edges, so that, and this is, you can think of this as a privacy thing where you can never observe what's happening beyond a certain point on a certain subset of nodes, and then reconstruct and then check what the scores look like. But I guess the main take-home message here is, you have higher with the proposed methods, you incur more error, but a better F1, which means you're recovering the structure in the better sense. But again, these are like very initial experiments. And something we also did was, so we recovered these graphs, right? And in this case, we recovered 3, so our value of R is 3. But what we also, something which can also be of interest is to see what do these graphs actually look like, the ones which are recovering. So we run them through some network science metrics like graph entropy and the number of connected components. And it seems that, well, if you impose more graph structure, there is a less diversity in the degrees, which means that you have, well, so you have more nodes with higher degrees or more nodes with lower degrees, which of course, depending on how you're looking at it, can be quite interesting. And it also leads to more connected components. So see, the connected components is like the average value is still increasing, which means you have more disconnected graphs. And for the end-on data set, so this have, and for 3 components, we give the picture of what are the components we are recovering, and just to contrast with what the unconstrained problem and what the symmetric BTD recovers, you see that there is clearly quite richness in the structure which we are recovering. Whereas unconstrained, well, it recovers exactly the same thing. And even with SVTD, yeah, you see that if you want to really interpret dynamics in terms of actual graph structures, there is, like with low rank models, you can only go so far, I guess. So yeah, so this was some of the results, and we also did some tests on SVM graph where we compared with another very famous tensor decomposition method, the CPD method, where we compared with by keeping the same number of parameters, and we have, like, so we see that when we have very little data available, the proposed TGD tends to do better, but as you have a lot of data, then CPD tends to do better when it comes to both NMEC and the F1 score. So that's something we are also looking at, and we see similar trend even on a temperature sensor network data which we did. And yeah, so I guess these are in general the preliminary results which we have. And it's a two-way decomposition, helps recover structure at the cost of reconstruction error. And of course, in future work, particularly interested in how do we work with alternative priors and to link it to blind source separation problems, spatial independent component analysis, and these kind of things. And of course, from a more theoretical perspective, how, because we do want this recovered components to be unique, because you want to say, okay, these things are indeed contributing to the dynamics and not something else. So under what conditions do we have uniqueness, recovery, and identifiability? So yeah, with that, okay, yeah, I think we're done. Thank you.